and there are some very interesting connections, say when you ask about can we use localization to protect, for example, topological phases or topological order at finite temperature, or when you close the bulk gap and so on, which usually is not possible if you have thermalization, right? So there will be a useful outcome of many-body localization, and that's still an open field of research. What exactly you can use it for? How robust is it? How do you use it best? In which kind of protocols? So to come back to yesterday's discussion, I showed you that. So when you convince yourself that many-body localization should be there and the golden rule is breaking down, then transport is not there because you have actually an extensive number of local integrals, and that you can construct them either perturbatively or non-perturbatively, as I will sketch quickly today too. And then we came to an expression for the Hamiltonian in terms of these local integrals. And yesterday I called them I alpha, and now I call them more suggestively n alpha, because I want to think now of disordered electrons with interactions. And now if the disorder is strong enough and the interactions are short range and weak, then we have these local integrals of motion. And so these are generalized occupation numbers of fermionic orbitals, but it's not single particle orbitals, it's sort of dressed orbitals, so that there is some electron plus certain electron hole excitations. But what is interesting is that this stuff now truly commutes with the Hamiltonian. That means this quasi-particle here is now exactly preserved, that has an infinite lifetime. And I mention that because you may know Fermi liquid theory, which is you take free fermions with a Fermi surface, then you add some interactions, maybe some disorder if you want, and then you have these quasi-particles that look a bit like plane waves, but they scatter from each other and they have always this finite lifetime, which goes like t squared over EF in a Fermi liquid, right? And now, when you crank up the disorder, of course the plane wave character is completely gone, but what you gain is that you get quasi-particles that have now an infinite lifetime, and they are just sharp. And you can even construct a creation operator that puts you a particle into this quasi-particle state, and that's somehow something quite exciting, that you can get a Fermi insulator instead of a Fermi liquid, where quasi-particles are a sharply defined concept. Right. So that's when, in particular, when you're interested about electrons, is an interesting view of many-body localization. Then I want to comment once again about dephasing, which was maybe a bit fuzzy yesterday. So the thing is, if you prepare an eigenstate of the many-body localized system, and so you fix these n alphas or the I alphas to have precise values, then there is no dephasing. Then a given quasi-particle alpha sees a certain local field, which is determined by the values of the other integrals of motion, and you precess exactly at this field if you make a superposition of I alpha being 1 or minus 1, okay? But you can never prepare an eigenstate in an experiment. This is just completely impossible. So what you can prepare in an experiment is maybe a biased superposition of eigenstates, where you don't take just any eigenstates, but maybe there's some bias to, say, having all spins up, or a homogeneous density, or a density wave or something. But there will still be an exponential number of eigenstates here. They may just look relatively similar in these eyes, but not completely a delta function on one eigenstate. And now you can ask, what is the local field that a certain quasi-particle, which is still sharply defined, what is the local field that it sees? So how does it interact with the rest? That's just a derivative of this expression with respect to n alpha or I alpha, and then you get an epsilon alpha or h alpha That's the local field that is there independent of what the neighbors do, but then, sorry, here this epsilon alpha. But then you have interactions with other integrals of motion and even more than one and so on. And the interesting thing is that if these interactions fall off very quickly and are small, then this has still some interesting structure. So the probability distribution of local fields over these eigenstates looks a bit like that if you have strong many-body localization. In principle, you see a local field that is more or less this term here. But then, depending on what your neighbors do, you see some side peaks, which are displaced by something of the order of this term. And then there are further side satellites that are, or a resolution of these peaks that you actually see here, that live on this scale. And if there is a strong separation of scales, then you get some hierarchical picture of local delta peaks of local fields that you see. And now where does this show up? If you now look at the spectral function of this local degree of freedom I alpha, so essentially if you look at the local spectral function of the central degree of freedom that pertains to this I alpha, what do you see? You see exactly a spectrum like this. You see a sort of a bunch of delta functions that are grouped together but have a finer and finer structure. This P is, yeah, so this is the distribution of local fields that you see when you, so you look at the spectral function. That means you ask for the eigenfrequencies that you see when you flip the spin I alpha. So you ask what kind of transitions can I make, and then you see that the transition energy depends on which eigenstate you are in, and so you have to basically, you get the weighted sum over possible transition energies, and for each eigenstate labeled by these I betas, you get different transition energies. Right, so you will see that that you can have a transition energy. Well, you always get this contribution, but then you get contribution from interaction with your neighbors, and depending on what your neighbors do, depending on which part of the superposition you're looking at, you get different transition energies, right? And yeah, so this is what I write in here is dH by d I alpha, right? And here I forgot to write the probability of being in this particular eigenstate, right? So this is a weighted sum of delta functions. In each eigenstate, you see a different local field, a different excitation energy when you flip that spin I alpha. This. No, I'm looking what energy does it cost me to flip the spin I alpha, and that the answer depends on the other integrals of motion, and so I get a weighted sum over these configurations for the excitation energy, right? If I had a non-interacting system, if I had an Anderson insulator, then there would be none of these terms, and then there would just be the energy of the single particle orbital, and I would have just one delta peak there, right? Yes. Yeah, roughly, yeah. Mm-hmm. Right. But so that's the trouble of MBL, that it's not as simple as Anderson insulator. So this would be just the Anderson insulator only. If you had no interactions, you would have only this term. But because of the interactions, you still have integrals of motion, but you have this knowledge of what the others are doing nevertheless. And that gives you this structure of possible excitation energies. And now this has implications on the entanglement spreading. So if I take a small subregion or even just one spin, and so I have my big system, and I look at this region A, and I look at the reduced density matrix as a function of time, and I define SA of t as minus trace rho AT log rho AT, right? If I were non-interacting, this would not grow much. This just saturates because there's some single particle localization around here, and that limits the amount of entanglement that you have. But here, because you have your local energy depends ultimately on all integrals of motion out here, this starts spreading slowly and grow and grow and grow, but very slowly. Actually, this grows logarithmically in time with a typical, with a typical energy scale given by this term here. So why logarithmically? Because on a given time scale, you can resolve only, say, a frequency scale which is 1 over t, right? So at short times, you don't see any of this fine structure. You see essentially only this term, and the rest is unresolvable to you. And that translates into you don't have information on your neighbors yet. And so there the entanglement entropy is essentially 0. But then if time goes on, you have a better resolution on energies, and maybe you see this. And that means that you can distinguish what your nearest neighbors are doing. And that means that you're entangled with your nearest neighbors. The behavior of your local spin tells you what the environment is doing, and that means there is an entanglement. And so you gradually pass information or lose information to your environment. In order to know what your local spin is really doing, you need to know more and more about the environment. And that spreads logarithmically because these interaction terms decay exponentially with distance. And so if you want to know something about a larger distance, you have to wait an exponential time until you can resolve these small energy scales, right? It's true that the local integrals of motion have this exponential decay, and that's related to these couplings being exponentially decaying. It's all related, yeah. Exactly. Right. So, and this has to be contrasted again to the ballistic growth of entanglement spreading in thermalizing, in most thermalizing systems. So you gain a lot in terms of keeping entanglement under control, but nevertheless, if the time goes to infinity, then SA becomes actually volume law. So it will scale like the volume of A. So whereas if you could prepare an eigenstate, then the entanglement entropy with the outside is only given by the integrals of motion that live on the boundary here, and that would be area law. So if you had a many-body eigenstate, which is essentially impossible to create in a lab, then you would have a surface of A here in the infinite time limit. But if you have a superposition, you will always entangle also the spins inside with the outside due to these interactions which are not zero. Okay. So, and that came a bit as a surprise. I think people didn't necessarily expect that, but numerics showed that you had this logarithmic growth, and then eventually one understood that from this kind of representation. But if you just had, say, the perturbative notion of many-body localization, you would maybe not have guessed that. So this is a real good tool to have in your mind to understand dynamics. Right. Okay. Right. Okay. Mm-hmm. Yeah. Yes, thank you for this question. Yeah, so ground states have a so-called area law, or they have entanglement of small regions with the rest that is only proportional to the surface because there is a finite correlation length, and in the ground state, degree of freedom only knows about other degrees of freedom up to a certain length, and so there is only a certain layer around the surface where inside and outside are correlated. But at finite temperature, where you have a lot of excitation, there is going in and out, and in a thermalized phase, this expression tends to, as you know now, goes to rho equilibrium, log rho equilibrium, and so this goes to the thermal entropy of the region A, and that is of course volume proportional to the volume, right? And now MBL is exactly killing this, right? It kills equilibration, and if you're looking at an eigenstate, then again you're like in a ground state and nothing can move. You have only one set of correlation between inside and outside, so there's only one of these terms, and therefore there's only an area law entanglement. Then you need a finite amount of information to describe what the outside does to your inside. But as soon as you start superposing a lot of eigenstates, then you need again more information, and then you go back to volume law. But the volume law here, the proportionality constant, is not the same as here. Here it's basically maximal. That's the maximum that you can get at a certain energy density. And here it will be sub-thermal, but still proportional to the volume. And if you like a challenge, you can try to figure out how this prefactor looks like and how you could compute it. I've thought a bit about this in the beginning of the week, and I think it's a difficult thing to really compute, but in a certain limit of strong localization, you can at least figure out how this scales with quantum fluctuations or with the scale of J. So maybe that's something you like to think about.
So maybe if you're excited by the localized superposition of states,
Mm-hmm.
because you cannot excite the single eigenstates.
Right, yeah. So you will always have a volume law, but this prefactor you can have pretty small actually. Yeah. Good. So, right. Now, so I want to get to the really important thing of how we protect topological order, or how we can maybe not, and what is open there. But it's also important to me that we discuss rare events and this phase diagram that we had yesterday once more. So there was this perturbative kind of argument that said that there is a phase transition between thermalizing and MBL, maybe, and it could be something like this, and then there was 1 over lambda or 1/2 here. And the fundamental question was, is something like this possible? Is it possible to have a sort of a mobility edge? So down here nothing moves, and then as you increase the energy density in the system, all of a sudden you open so many channels that it starts delocalizing. Is that possible? In a single particle problem, we know that as a function of energy you can have that at low energy usually you are more localized, and then if you give more energy to the particle it can delocalize because it explores more density of states essentially. But here the problem is fundamentally different in the sense that the energy is actually not bounded. You have an essentially extensive amount of energy proportional to the number of particles, and so you cannot constrain the energy locally to be below some energy density times local volume. There can be a rare fluctuation where you have as much energy as you want in a volume, and so you know, in real space you could have a region. So this is my space. Everything is pretty cold, but there could be a rare fluctuation where here you have enormously much energy, and energy conservation doesn't prevent you from doing that, and you wouldn't be off shell in the sense of you know, you would have to borrow this energy from nowhere, as you would have to do in a single particle case. Here you have many particles, and if you take their energy together and you give it all to this region, it's perfectly fine with energy conservation. And now suppose this region here looks as if it were up here, right? So this is much bigger than the purported TC. And now you start doing perturbation theory here, then you see that inside this region there's no chance perturbation theory can converge, because you know that if the whole system is up here, you're thermalizing. So perturbation theory is certainly not working here. But as long as you're just working inside this hot bubble, you also don't see perturbation theory to converge. And actually you can construct perturbative in a perturbative expansion configurations that are just moving this hot region around, and perturbation theory will never get under control. And so at the very least you can say, even if I'm down here with the overall, say, I should actually rather write energy density here than temperature. If my energy density, even if it's down here, and typically if I'm working in regions where I don't have a hot bubble, it all looks benign, I can create in high order of perturbation theory a region like that where I have a lot of hot particles and high energy density. Then locally it looks like this, and there perturbation theory will be out of control. And there's nothing that prevents you from getting there in finite steps of perturbation theory. You can only say, well, this looks like a pretty suppressed process, and maybe I should not worry about it, but mathematically speaking, you don't have this under control. The only thing that you can really have under control is if there is an upper bound here, if basically you're on a lattice, and if you can argue that even if you have infinite temperature on the lattice, you're localized, then you're sure that also at lower temperature nothing will happen. But if you want a transition as a function of energy density, or as a function of particle density for that matter, you always have this problem. And so these are these rare events that might, or rare bubbles that might induce delocalization. And for the, I mean, we are not sure this. I mean, there's certainly no proof that this always happens. But what you can say for sure is that no perturbative argument can kill this. So under that circumstance, you can always construct a network of resonantly coupled configurations, namely that percolate to infinity. So, and if we take that as a criterion for delocalization, then we would be done. But so that's to infinity. Namely, I can make yeah, of resonantly coupled. Oh my God, coupled configurations. Yeah, maybe I should not write what I'm talking, but just talk. So, resonantly coupled configurations that percolate to infinity. So what you can, in a finite number of steps of perturbation theory, you can create yourself such a thing that is very hot, and then you can argue that there are resonant matrix elements between this and that and this and that that goes out to infinity. Basically, you can use random matrix theory to describe what happens in such a thermal blob. Then you estimate the matrix elements for displacing the blob a little bit, and then you find that the matrix element is always bigger than the level spacing within the blob, and then you figure out that this is all resonant, and then you have a resonant network because this bubble can go to infinity. Well, usually the bubble will be heated up by its environment. If the environment is thermal and now you make a cold bubble, well, there's nothing that prevents heat to flow in. You mean when this hits some cold region, so to speak? Yeah. 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 Okay, so if you're in one dimension, then you cannot avoid the cold region. In higher dimensions, you wouldn't care, right? And you go just around. But in one dimension, indeed, then you have to argue, okay, then maybe a too small hot bubble will die there. But then you have to make your bubble bigger, and then you say, then this will not care about this cold region. And so you always find, it gets crazier and crazier, but you get finite events that you never can control, basically. And you may say, okay, if I want to get so and so far, then I need a rare event that is so and so rare, and if I want to get further, I need something that is even rarer and bigger and so on, but you can always construct something that is not under control. And the big challenge is, I'm not saying this is true. I believe it is true because I don't see a way out, but it might be that this is wrong. That, this hot bubble can, of course, also decay. It can lose its energy, but the thing is that if it then should localize, this energy is still distributed around the original position, and it can come back, and there is some, Poincare recurrence time to come back, and then it can move on. But there's a fundamental flaw maybe in this reasoning, that when you have a resonant network to infinity, then you delocalize. We know that this is not true in, say, two-dimensional Anderson insulators, where you have weak disorder and strong hopping. If you do the naive reasoning, you say the hopping makes everything resonant, right? The whole lattice is resonant, so I should just go to infinity, and nevertheless there is weak localization that eventually imposes a very large but finite localization length. And there is special physics going in there, that is this quantum interference of coming back to the origin. And something like this might maybe happen here too, but nobody has found that. So it would be great, say, if somebody can come up and say this is wrong, and MBL is actually stable here, and there can be a mobility edge because of this and that phenomenon. But so far we don't know this. Yeah. That is not excluded, but that's not something that is particularly helpful for the process. I mean, you don't want to rely on two rare events meeting each other, that's even rarer. And so you want to construct something that relies on one thing that goes away. And a very simple instance of that kind of picture we worked through in low dimensions, in one dimension, for example, where you know that all single particle states are localized, but at high energies they get more and more delocalized, but never fully delocalized. But then you can ask yourself, okay, if the states are localized like this, and then they get bigger and bigger as you go up in energy, but I'm working down here with the Fermi level and I have particles down here. Can I not just forget about this up here? Because this is always localized. The answer is no. If you put the particle up here, then it has such a long localization length and so fine level spacing up here. Actually, there will be so many states here that even a very weak interaction with cold particles down here that are excited is enough to dephase this and to make this resonant. And then you can basically argue that you get delocalization just from one hot particle that scatters from the cold stuff down here. And so that's the simplest example of such a rare bubble, and we are pretty confident that this at least is correct. People are more worried whether this is still correct if this is not a single particle that is hot, but if it's 10 particles that are hot. But I think it is still dangerous. And so if you buy my argument that this is a resonant network and it delocalizes, then the phase diagram has to look like this, and this is just a crossover. Okay. Yeah. This will become essentially activated, so this will be e to the minus some delta over t, and this delta is basically the free energy cost or the energy cost to create something like that. So this can be horribly, so this would be conductivity or heat conductivity. This can be horribly small, but it would still be finite. Yeah, so when we are talking about these rare events, these are also the things that make disorder-free localization, unfortunately, just a crossover. So I told you that there's this interesting idea that you could dispense of the disorder and just say, well, if I have interesting interactions that simulate disorder through the, through the interactions with your environment, a bit like here, right? So I have, for example, spin interactions that are longer ranged, and so a given spin sees such a complicated field from its neighbors that if it wants to flip with its neighbor, there will always be an energy mismatch because the environment is so complicated. You could think that you could get many-body localization just through strong interactions. And that's almost, it seems almost true, but the caveat is that if you have no quench disorder, there may always be some rare regions in space where your configuration is not complicated but extremely ordered, or for example where all spins are pointing down, or there are no particles around, or something like that. And in such a region there is essentially no disorder, and that's a rare bubble like this where ergodicity is restored. And if this bubble is large enough, then you can again make this kind of argument, and such a bubble would be mobile. And then you come to the conclusion that that you cannot probably have a true transition without quench disorder, because you cannot avoid this kind of effect. So probably MBL becomes a crossover at the MBL finite T transition. Finite T transition is a crossover, and likewise many-body localization without disorder would probably just be a crossover. But the crossover here can be so extremely strong that you can just maybe not care about that this is not a true phase transition, but just something like a glass transition where things become so slow that you say, well, why do I care about something so unlikely to happen? I'm happy with the phenomenology that happens on time scales where you don't see any of this. right? That's a bit the philosophy of MBL. But if you want to prove, if you want to be a mathematician and say, I can show there is no conductivity, then you are probably doomed, right? So to prove something like that. Okay. So with all these caveats, you might feel it is a bit, MBL looks very fragile. Does it ever exist, or are there always loopholes? And I want to at least give you one example where we basically know that it does happen, right? So we know at least something for sure, and that's a proof by John Imbrie for the following model. I just want to give you the flavor or the basic idea, and that should be enough. But it's good to have some solid ground, I guess. Also because it will teach us about the role of dimension, which so far we don't understand from the discussion we had. Okay, so he took the simplest possible model. It turns out he was smart to do so, because any additional feature would have failed him, I guess. So he took a one-dimensional spin chain with discrete lattice sides, so it's a chain, a lattice. It's not in the continuum. Strong disorder here. This is quantum fluctuations, weak. Arbitrarily weak, actually, and these are interactions so as to make the system not integrable. So this is the interaction part. Okay, so the idea is as long as this is very strong, this is not so strong, and this is weak, there should be MBL according to our wisdom so far. But he wanted to prove that. And the idea of the proof was to find a local, a quasi-unitary, quasi-local unitary rotation that brings the Hamiltonian into this simple form as we wrote down with the integrals of motion, actually. So he tries to find a unitary that then has the form like this. Well, as we discussed before, right? Where now the integrals of motion are called SZ. Okay, and so U is a unitary, and it's actually a product of essentially local rotations. So you find unitaries one by one, where you rotate this Hamiltonian and try to bring it more and more in this form. So you try to rotate away the off-diagonal terms in the basis of the SC. So you want to get rid of these terms, but when you rotate, you create some new off-diagonal terms, and then you rotate again, and the hope is that you can do this a bit in a Newton method-like fashion, or a bit like in CAM theory, that you always get rid of what is doesn't look integrable, and then you get closer and closer to this form. And he managed to do that, so he managed to show that you can do this in a smart way, such that it converges. And so what is the basic idea? I just tell you how you set it up, and then you can try and look at his paper and see whether you are interested to know more details. So the idea is basically the following. There are perturbative regions where this transverse term doesn't connect resonantly any configurations. So you look what are the matrix elements of this guy, between what kind of configurations in the neighborhood. And if you see the matrix element is always smaller than the energy difference, that's a perturbative site. And there it is easy to find a rotation that essentially takes this away, right? So you just define a perturbative in gamma over H and J, basically rotations that eliminate this gamma. So you eliminate it to first order, but then what remains is second order in gamma, and so it's very small, and then in the next step you rotate it again, and then it's fourth order maybe, and so on and so forth. But there are some spots where this doesn't act perturbatively, for example, regions where all the H are 0 or something like that, then you have resonant action of this guy. But these regions are kind of rare because you need that the level differences are smaller than the gamma, right? So there are some rare regions are resonant, and those you have to treat separately. So what you will do is you look in your chain where are these resonant spots where something happens. So you keep them out, and you only first rotate perturbatively here and here and here, and now you go back to these regions. Now when you rotate perturbatively here, then you renormalize the couplings of the degrees of freedom that sit here with these regions here. And actually, because you rotate here, you get some very weak coupling, but non-zero coupling over here from degrees of freedom that were further away, because you perturbatively admix some exponentially small weight over here. So there will be exponentially small coupling between degrees of freedom here and here, because of this perturbative rotation. But that could potentially be dangerous, because if this is a big ergodic spot, it will have a very small level spacing, and such an exponentially small coupling might still become resonant, right? So that's sort of maximum of H and J. So yeah. So it's easy to write out, to really define what this rotation has to be. You just do first order perturbation theory. You can work that out explicitly. Okay, so the thing is that these rotations create some exponentially small couplings to dangerous regions, and now you have to argue that this is still not so dangerous. So you go to these resonant regions and say, okay, if I have, say, 3 spins that are nearly in zero field, and therefore they are resonantly mixed, and the interaction and the transverse field that couples everything together here, now I get 2 to the 3 states that are fully, thermally mixed in here, like a random matrix. Then I have a level spacing that is now 1 over 2 to the 3 in here, and that's a dangerous thing. If you couple to that too strongly, then the level spacing is so small that this coupling might be resonant. So in particular, expect that, for example, the next spin here is likely to be resonant, right? And maybe the next spin also. And now if you did things too naively, and if you didn't first rotate here, then you would say, well, if I have a big enough region here, it has such a small level spacing that any coupling will be enough to make it resonant, then this will be fully mixed with this resonant region. The resonant region is bigger, now it has even a smaller level spacing. Now the next degree of freedom will also be resonantly mixed in, and then you could come to the stupid conclusion that just everything becomes resonant whatever you do if you have a sufficiently big spot in the beginning. And that's a fallacy. That's certainly not true. What you should do first is that you rotate this into diagonal form as much as you can, and then you are left with these small exponential couplings. And when you now start eating degrees of freedom that become resonant, then you should remember that the only coupling of this guy to the region to the right is through this very small coupling. And it's not through a strong coupling with this degree of freedom still. Okay, so the coupling is weak with the distance of this degree of freedom to the resonant spot. And now you can ask, well, if this resonant spot is growing because it incorporates resonantly other degrees of freedom, do I have any chance that it will never include this degree of freedom into its resonance region? And the answer is yes. You can protect this degree of freedom from being eaten by the resonant spot. And why is that? So because this coupling that remains as a function of distance here goes like e to the minus r over some scale psi, and the stronger the disorder and the weaker the quantum fluctuations, the shorter is this psi. And now you say, well, let this resonant spot have grown up to size r here. And now I ask, is this coupling going to be resonant? Well, what do I have to do? I have to compare this coupling strength, which has a certain operator that acts here. So it goes like e to the minus r over psi, and I have to compare that essentially to the level spacing of whatever has developed here. And if this is a fully mixing thing, then the level spacing will just be the bandwidth of this region divided by the number of levels that you have, and that is basically 1 over, say, 2 to the r or 2 to the 2r of this region. There may be a further suppression of the matrix element because you have to estimate it by random matrix theory, and there may be a further square root of the dimension of that spot, but let's leave that away. What you see is that there's a competition between a matrix element that is exponentially decaying and a level spacing that is exponentially getting smaller. So this is the level spacing in this supposedly growing resonance spot. And now the question is, does this resonance spot just become infinitely big and does everything get thermalized? And the answer is no, you can control that. If this decay here is sufficiently big, if gamma is sufficiently small, then VR will always become smaller than delta R, and that means you are perturbative. And that means that the growth of this bath here, this ergodic spot, can grow to a certain distance where this is still smaller than that, but at some point it will stop growing. So even if you have a dangerous region where you cannot control perturbations here and where you have to fully diagonalize the Hamiltonian, at some point you will become perturbative again, just because you were smart enough to first do the perturbative rotations here and to make this coupling very small. And you get an exponential that is stronger decaying than the bath increases its efficiency. So just for correctness, here should be 2 to the r square root, but that only helps you. So this comes from, this is a random matrix type suppression of the matrix element, because you're basically looking at matrix element between random thermalized states in here. But you can clearly see that there is some some RC which is finite, such that when R is bigger than RC, you're perturbative. Okay, and that is essentially the idea of the proof of Imbri, that you can make a safety color around dangerous regions, and the safety color is finite, and outside you can treat everything perturbatively, inside you do whatever you want, and then you show that there are only a sparse set of such resonant regions, and they are not enough to delocalize you. Right. Yeah? Mm-hmm. Yeah, this grows just maybe like R. So this is subdominant. So before the break, let's now see where the dimension plays a crucial role here. So if you try to do the same thing in higher dimensions, then and now you have a resonant spot here that you want to control, then again you would say, okay, first I'm smart and I perturbatively rotate everything that is out here, and so a degree of freedom will be coupled to here again only with something that goes like e to minus r over some psi. But what is now dangerous is if this spot starts to grow, then its level spacing, which is the inverse of the volume of the Hilbert space inside the spot, is going to grow not like linearly in the radius, but it grows like, so this level spacing goes always like exponential of minus r to the d actually. So before we had exponential minus log 2 times r, right? The log 2 is sort of the entropy density at infinite temperature. So here there would be an entropy density of infinite temperature 2. Then it's correctly dimensionless. So the problem is that this goes like r to the d, whereas the matrix element still goes like exponential minus r linearly. Okay. And what you would want to control your thing, you would want that VR should at some point become smaller than delta R as R becomes big, right? And now you see that since this becomes exponentially faster slow as R goes to infinity, you can never win, right? And for quite some time, Imbri thought that this was just a technical problem because somehow this growth of the spot cannot be physical or so. But I think over the years, more and more people got convinced that this is a real problem, that it's actually likely that this spot thermalizes the first color, becomes bigger, thermalizes the next color, and so on, and it becomes a bath that becomes more and more efficient in thermalizing what is around it. It may take more and more time to thermalize what is around because the time scale is the inverse of this coupling. So if you want to thermalize something out here, you have to wait quite a long time, but eventually it will happen. So it's just a question of time, and there's nothing like in one dimension that will stop this, right? So if there's no fundamental flaw in assuming that everything becomes thermal inside this region, then it will just grow and grow and grow. And so this we call somehow a quantum avalanche. And they seem to be excluding MBL in dimension bigger than 1. But I have to say, so this being said, what does this rely on? This relies on the presence of a resonant spot that is sufficiently big so that it can start to grow. That means I need an original region where, for example, the randomness is extremely low in sufficiently big space, right? And if you have quench disorder that is uncorrelated, then there is always a finite probability of something like this to happen. And if that is there, then it might grow like a cancer, no? Except in one dimension. But you can have either correlated disorder where you just suppress such things and give them essentially no probability whatsoever, or you work actually not with true disorder, but you work with quasi-periodic potentials that look like disorder but actually are deterministic, and where such things just never happen. Because the HIs are not random, but if you take them, for example, like h times cosine of alpha I, and alpha is incommensurate, say the golden ratio or something like that, and you make h big, then this looks like a random sequence, but it's a random sequence where you never have a succession of a lot of zeros or near zero numbers. It always goes up and down in a random fashion. And so if you take quasi-periodic potentials in higher dimensions like that, then you never have these dangerous spots, and then you still can have MBL even in higher dimensions. So and that's maybe something very interesting. So if you have quasi-periodic potentials, it's not a disorder, it's just something that suppresses resonances, then you can maybe have MBL also in d larger or equal to 2. And that's exactly actually like how Immanuel Bloch or other people with cold atoms create quasi-disorder. It's relatively easy to make quasi-periodic potentials, maybe easier than speckle potentials that are disordered. And so so when I say MBL needs low dimensions, that's maybe true for just randomly disordered systems, but you may have the phenomenon still if you suppress your resonances not by disorder but by quasi-periodic potentials. Okay, and now we are ready for a break, and after the break we'll discuss the protection of nice orders by MBL, and that will be the final cherry on the cake. Good, thanks. Okay, so now we want to see whether we can use MBL to get something really exotic or something that is not possible in equilibrium, apart from just storing density patterns. And so we saw that there is dephasing, so quantum computation with just these integrals of motion is probably not possible, but you could hope that you can protect topological order by MBL, and topological order is interesting because when you have anyons and you have interesting braiding statistics, then you could do topological quantum computation, and if this is helped by MBL, then it would have a real nice feature. Also, what I will show you first now is that you can use MBL to get stuff that you cannot have in equilibrium, namely you can protect symmetry breaking in low dimensions, in one dimension, even at finite temperature. Can somebody remind everybody why you cannot have symmetry breaking in equilibrium at finite temperature in one dimension? Mermin-Wagner? I wouldn't call it Mermin-Wagner, but what is the physics? No. Yes, but I didn't say anything about continuous. So why can you not have easing order in one dimension at high temperature, at finite temperature? Yes, but a bit more in detail. Yeah. Yeah, you can do, right? Yeah, you can do a lot of calculations, but you can also just ask what is the physics? What is the physics? Right, yeah. If you break your order somewhere, that costs some energy, but that comes with a certain density, right? The e to the minus this energy over t. This will happen with this probability, and then if you break it here and here and here, then this doesn't know anything about that anymore because there are defects in between, and you have nothing to go around the defects. And if these defects or these domain walls can be anywhere, and they will be anywhere because they are mobile, then they destroy any correlation between here and here. And now how can we use MBL to circumvent that? Right, so you can still have your domain walls, but if the domain walls are stuck and do not move like they do in thermal equilibrium, because you just say they can be anywhere, if they are stuck at their initial conditions, then you may have a random relation between here and here, but this relation is stuck in time, right? And then you have sort of a spin glass order, but you have a long range order of orientations. So let's go through this pretty quickly. That's the essential idea. Once you get the idea, you just have to work it out for yourself. By the way, there's a very nice review of this topic, and maybe I don't have enough time to discuss everything, but I warmly recommend you this. It's very nicely written, and it covers much more than I can tell you about, and it also opens a bit the perspective of what is not yet resolved about protecting topological order, in particular, interesting topological order. And so if you look for interesting problems in MBL, then that's maybe the place to look. Okay, so let's look at this model now quickly. So, yeah, that suffices for us. So, there is a disordered transverse field. There's an Ising coupling, which is also random, say, and there is a transverse coupling that I take non-disordered. Okay, so if I write down this, do you know how you would solve that? That's transverse field Ising model. Even with disorder, you can Jordan-Wigner that. You get Majorana fermions that are free, then they will be localized because there's disorder, there's Anderson localization. It's either weak or strong, but that would be a single particle problem. It's nevertheless interesting. Actually, Daniel Fisher realized that you maybe should not do Jordan-Wigner, but you should ask about physics, and he invented strong randomness RG. So he said, if these are strongly distributed and sometimes big, sometimes small, then let's integrate out the strongest coupling. If this is strong, then I say the two spins point in the same direction. If this is strong, I put the spin along the local field, and then I take out this degree of freedom and I renormalize the rest, the couplings, and then I get the flow in coupling space, and then I get a strong randomness RG, where I see that the distribution of these couplings becomes stronger and stronger as I let the RG flow. And then there's a very nice insight in the phase transition that you can have between a ferromagnetic phase and a paramagnetic phase, depending on who is winning. And the critical point is where log HI average is equal to log JI average. Okay, but in terms of MBL, what we would want to have is not a single particle problem in principle, but interactions. That's why I put this term. And now, what would you say if I make this term very strong? Is there MBL? Is there localization if I make this term strong? Or this encapsulates actually interactions between the free particles that you get here from Jordan-Wigner. If you do Jordan-Wigner, you rewrite this term, you get an interaction term. If you make the interaction term too strong, then everything thermalizes and there is no MBL. But if you make this weak enough, and you could estimate how weak you have to make it from the reasoning that we had in the last lecture, then there would be MBL transition on the lattice, then everything is safe. At infinite temperature, there would be a transition to an MBL phase. And so as a function of J perp over, say, max of these H and the J's, something, variances of those. If you make this strong, then you have just a thermalizing phase. That's not so interesting, but then there would be somewhere an MBL transition, even at infinite temperature here. And now the question is, what happens as a function of this parameter? This disorder versus that disorder. So this is J perp as compared to the maximum of these disorder strength. So here it would be thermalizing and here it would be MBL. But the interesting thing is that even in the absence of this, you have this strong randomness phase transition between paramagnet over here, where the H dominates, and the ferromagnet, where this term dominates here, right? But both of them are MBL because both are free fermions that are localized and have weak interactions. But inside the MBL there is still a phase transition, and it is likely that this phase transition persists up to some finite value of the interaction. Yesterday we called this sort of lambda. And then there would be some phase boundary maybe like this. So if the two compete much against each other, then the third guy has maybe the best chance of intervening. So maybe this is natural to have something like this. So you expect a phase diagram like that. And what does it mean? So in this phase, the eigenstates would be preserve some ferromagnetic, some Ising type order. So you have actually and here you have just sort of disordered spins. At least, just a second, yeah. So, yeah. Here, I think that's a matter of debate. What exactly happens here, and whether it. I found it a bit too exotic to think about. It's not my private turf, so I'm not sure. But this is certainly safe. Right. So let's discuss actually how the eigenstates look over here. Here you have basically just a random pattern in x direction, which is weakly perturbed by that, and the interactions are not sufficient to make you thermal. But over here we have maybe an interesting structure. And so why is there actually anything interesting to say at all? Because the Hamiltonian has actually an Ising symmetry, right? So you have the operator which flips all the spins from Z up to Z down. So you have the parity operator, which is the product of all sigma Ix that commutes with the Hamiltonian, right? And either you break this Ising symmetry or you don't. And the thing is, in equilibrium, you can never break this symmetry except at zero temperature. here, by MBL allows you essentially to localize the domain walls, which destroy that. So this is the actually Landau-Peierls argument. Peierls says in equilibrium, domain walls disorder the spins. Right. Because they are mobile in MBL, they can be localized and then they localize. So potentially at least, right? Okay, so the eigenstates, the MBL eigenstates here, if this is the strongest term, how would the eigenstates look like? Essentially, there will be some patterns of spin up, spin down, depending on what this guy wants the spins to do. This doesn't even have to be ferromagnetic, it can also be antiferromagnetic. But so in an excited state, sometimes you will put the spins parallel according to the J or anti-parallel. It may just cost higher energy, but if this is the highest, if this is the strongest term, then you can also just construct excited states by putting this into the unfavorable configuration according to the coupling, and then you perturbatively treat these terms. Okay, for example, there is a state like that, but there is also the other state where you the Ising flipped state, which has essentially the same energy, and they are coupled to each other through the extensive action of this term, and so there will be a tunneling matrix element between this and that, which goes exponential in the system size, right? Essentially. And so the exact eigenstates will be Schrödinger cats of such configurations, right? But if you prepare the system in this state, it will take exponentially long time until you see this state coming up until the system flips over. That's like in spontaneous symmetry breaking too, like in the ground state of the transverse field Ising model. If you prepare the ground state of ups, after exponential time you see a superposition of up and down because there's an exponentially small tunneling, right? Here it's the same thing, but because of MBL, because there is heterogeneity in these JIs and these terms are weak, these domain walls here can now not move resonantly. If you had no disorder, then they could just move without any energy cost essentially, and they would move around, and then they would wash out the particular pattern that you see here, namely that this spin essentially is always opposite to that one. If the domain wall could move, then you would lose that immediately. But if the domain wall is essentially localized, because moving it by this term, for example, would cost you energy. So if you want to move the domain wall over here, then you have changed say this J1 and J2 are not equal, then you change the energy of that term, and you gain only this kinetic energy, and if this is much weaker than that, you will not move the domain wall, right? And so the domain wall will be dynamically stuck here, and the only real thing that will happen at very long times is that you flip everybody together, and then you are resonant again, right? But only at this exponentially long time. And so you see that you can preserve Ising order of some a bit strange type. I mean, there is long-range correlation between the spins. If you look at SI plus RZ, then this will, even at t going to infinity, this will not be zero. But it will not have a definite sign. It depends on the initial condition that you prepared. This will be sort of spin glassy, like that. This will be randomly positive or negative, but it will not change in time. So that's why people say actually it's sort of spin glass Ising order that you can preserve. Now this is discussion of eigenstates, and I told you now many times that eigenstates are just a theory concept. But now you can ask, is that useful for anything? Well, yes, it is. If you prepare an initial state, like all spins up or an antiferromagnetic pattern, and then you ask, what will I see in the MBL phase at long times? It depends whether you are here or here. If you're here, then you see this easing pattern still at long times, but if you are here, even though you have MBL, you don't see the easing pattern anymore that you have initially put, or you don't see it in a long-range manner. This would go to 0 if you are in the paramagnetic phase. Right, and in the ferromagnetic or in the spin glass phase, you would preserve this long-range order, even though you don't prepare an eigenstate, but you prepare a superposition of eigenstates, but each of them has a tendency to preserve this, and then you will retain the initial order at infinite times. Yeah. Yeah. Right. Yeah, that's true. So that is as meaningful as this expression is. I mean, you can imprint a certain fine pattern, and it has a persistence. If you can resolve this pattern, if you can read out the spins again, then essentially just tells you that the local spin is conserved to some degree, and this is of course then the disconnected part of the correlation function that survives. I find it's more of a curiosity than something very useful, but you see, it's something that can happen with MBL that cannot happen at equilibrium, and so that's at least one thing that you should remember. But I think what is more interesting now, I think that's more or less what there is to say about this, is can you protect topological order? That's much more useful, because topological order is maybe something that we want to use for quantum technology or so. And unfortunately, the answer there is yes, but only sometimes. Or at least there seem to be some obstructions, and and I hope there will be some interesting loopholes in what I'm telling you now, but so far this is an open thing. So let's go to topological order. So unfortunately, this local integral of motion structure is not compatible with many types of compatible with a lot of topological orders, but with some, okay. But maybe those that survive are not the interesting ones. So an example is the Heisenberg chain, and I should mention that because of yesterday's or the lectures of Marcello. So if you have antiferromagnetic chain, but now with disordered couplings, you might naively say, well, this has all the ingredients that I need for many-body localization. It's interacting, but it has this randomness here. But it also has SU2 symmetry. And you can ask, what does the symmetry do? Some topological order, like here, is protected by symmetry. It was not necessarily exactly the SU2 symmetry here, but this Z2 symmetry. But you can ask, is symmetry affordable to have to have MBL. Here we see Ising symmetry is okay, but what doesn't seem to be okay is if you have a non-abelian symmetry. So yes. Yes, okay, well, yeah. I mean, just spin rotation symmetry, I mean, okay. So if you have a non-abelian symmetry group, MBL with local integrals of motion that span the whole degrees of freedom seems not to be compatible. And the reason is relatively simple. So the thing is that the local integrals of motion transform under this non-abelian symmetry group, and they usually there will be some integrals of motion that transform with representations of the non-abelian symmetry group that are not one-dimensional, and so there will be a multiplet of local integrals of motion that are connected by the symmetry, and that means that there is a degeneracy in the spectrum if you have that. So essentially some local integrals of motion must transform as multiplets, and that means not as singlets, and that means that that you can change the value of the integrals of motion without changing the energy. So there are non-trivial symmetry operations that will change your I alpha expectation values or quantum numbers, but they don't change the energy, and that means that there's an exact degeneracy associated with changing some integrals of motion. And since this will happen with a finite fraction of local integrals of motion, namely those that are not singlets, this means that there will be an extensive degeneracy in the spectrum, because you can change in quantum numbers and you don't change the energy. That means there is a degeneracy. And if you can do that in many places in your sample, and it doesn't change anything, that means there is an extensive degeneracy, and that cannot be stable to small perturbations. If you assume you have local integrals of motion, and now you make a symmetry operation, you get new values for the integrals of motion, but you haven't changed the energy, then it would mean that that you have exact 3 degrees of freedom hanging around. But if you think of, for example, 2 free spins that have just a zero Hamiltonian, well, there will always be some coupling that actually couples these spins, and that will lift this degeneracy. So these spins would be the local integrals of motion. There will be an S1 and an S2, and there will be an effective term in the Hamiltonian between these spins that is not zero, but there will be something like maybe symmetry invariant, but there will be some coupling, and this coupling will immediately split the eigenstates from a fourfold degenerate spin 1/2 Hamiltonian into a singlet and a triplet, right? And both of them are entangled. That means that these local integrals of motion that you thought were just local here will now split, and they will mix, and they will sort of delocalize here. And then you have a singlet, which would be benign, but then you have a triplet again, that's a multiplet again. And then there would be another local integral of motion here that is again degenerate, and that would again talk with this triplet and split the degeneracy in the triplet, and then you get the delocalization of your local integrals of motion. Yeah. If you have a symmetry of the model, then you cannot have local integrals of motion that would look like this. But now that would be a question to Marcello. I don't know the answer. Can you break the SO3 symmetry and preserve the topological order here? I'm not sure. Maybe. Yeah, I would think so. If there's a natural way of doing that. But if you want just the Heisenberg chain, then it would kill MBL in the strict sense of having local integrals of motion, because this extensive degeneracy is not compatible with local degrees of freedom. There will just be, you will have hybridization between these local integrals of motion that split this degeneracy, and then you have non-local, at least some non-local integrals of motion. Right. So then either you remove the non-abelian symmetry from the model, or your eigenstates have to spontaneously break that symmetry. That both are allowed, and if the symmetry that protects the topological order is preserved, and that is abelian, then you're fine. Then you can. But so it looks like you can at best protect abelian symmetries, and by MBL, or MBL is consistent. I should maybe not say like this. At best, abelian symmetries are consistent with MBL. So if you want MBL, then you have to either remove the non-abelian symmetry from the Hamiltonian, or you have to spontaneously break the symmetry in the eigenstates, a bit like what you do here if you don't allow the tunneling. Okay. And that happens, so it can happen that you have a symmetry of the Hamiltonian, the eigenstates spontaneously break that symmetry. That's not something that would not be allowed. Okay. Right. But now, if you have an abelian symmetry that you want to break spontaneously by the eigenstates, and it's a continuous symmetry on top, say some U1 symmetry, then you're again doomed, because now if the eigenstates spontaneously break that symmetry, then you have Goldstone modes around that configuration, and these Goldstone modes cannot localize, and that would delocalize you again. So this should better be so if you break spontaneously the non-abelian symmetry, then if it is continuous, then you get Goldstone modes, and that will delocalize again. So the best you can hope for really is that if you want non-abelian symmetries somehow to be there in the Hamiltonian, then you have to spontaneously break the non-abelian symmetries in the eigenstates, but you can only afford discrete non-abelian symmetries. And there are examples in that review that I gave of exactly this case. You have a non-abelian discrete symmetry, the eigenstates break them spontaneously, and that's fine. So that exists. At least there is something that you can protect by MBL. But unfortunately, what would be the most interesting thing, and with that I will then conclude, is if you wanted to do topological quantum computation, you would like to have something like a fractional quantum Hall effect or so, where you have anyons that when you braid them around each other, you change the wave function, even though the anyons are at the same place after the braiding, right? That you want a degeneracy of the quantum states that have a certain number of anyons. And so there would be yeah, you would store the history of your quantum processing in the way that you braid these anyons, but you operate in a degenerate space of ground states at a given number of anyons. Okay. Now, and it's known that this can only work at essentially zero temperature, where you have no anyons that you do not control, because if you have other anyons in the system, they can randomly braid around the anyons that you want to control, and then you don't know what is the braiding that you want to do. Okay, so usually these topological phases and their topological sectors are defined only at t equals 0, because at finite temperature you will have excitations that can cross the whole sample, they can wind around, and then you get into different topological sectors, and so it's not well defined anymore. But you could hope that through localization you stop this from happening. You would localize unwanted anyons. Okay, and there are papers that describe that. So you could hope to do that by disorder, Anderson localization of anyons. That's possible. Or maybe even you would try to use interactions, strong interactions without disorder, but that's even more complicated. But the trouble is, now you can ask, can I have interesting anionic systems? And what are interesting ones? That are those that have non-abelian braiding statistics. So maybe you know the toric code or so as a topological phase. They have these two types of anyons. When you braid them, you pick up a certain non-trivial phase, but it's just a phase. And so that's an abelian topological phase. And that seems to be perfectly consistent with that. But what you actually would want to do for quantum computation is that you have non-abelian phases where you don't get to the same wave function just up to a phase when you braid two anyons. And now that seems unfortunately incompatible with the notion of local integrals of motion. And the reason is very simple. So if you have your anyons like that, quantum computation, topological quantum computation would rely on the fact that when you braid one of those around the other, there are ways to do that such that the wave function here is not the same as before, not just up to a phase, but really something different. But MBL would tell you that every state can be characterized by local integrals of motion. That means if you measure here the integral of motion and here and here and here and here, then you know exactly what is your eigenstate and or what is the state of your system. But topological computation just would rely on the fact that you cannot tell locally that something has changed. It's only in the global structure that something has changed, and that is the beauty of this topological computation. So if you braid around here and everything looks the same locally, then MBL would say I'm in the same state, right? MBL would say there cannot be any non-trivial braiding if, of course, if the local integrals of motion exhaust all degrees of freedom. So that means that if I have a spin system with n spins, if I have n spins, then I would have exactly n Lioms. If I really nail down everything by the local integrals of motion, something like this is not possible. But this leaves maybe to some extent open that you would have n minus a finite number of local integrals of motion, which would sort of prevent unwanted anions to come up and travel around. But you could maybe still store some non-trivial information in the wave function that is not nailed down by local integrals of motion. I'm not sure this is a true possibility, but I think logically it's not yet ruled out, and there is some hope that something like that might happen, and that many-body localization could help you to protect that at finite temperature. And whether that happens or not, that is maybe a difficult question, but it's an exciting question. So maybe with that perspective, I would leave it at that, and thank you for your attention. Yeah.
So basically, if we have manual localization and the wave function is more localized,
Mm-hmm.
I wouldn't expect topological order because it's somehow closed.
Right.
Do you have any comments on that?
Well, that's basically the comment. Indeed, it looks like these are two different animals that don't like each other, right? But I mean, topological order, a simpler topological order, you can protect with, say, if it's the edge modes of a spin chain. If you are at finite temperature and you have no disorder, these edge modes have a finite lifetime. They talk to each other. Now you put disorder, and then you can construct these strong zero modes that you know, and these edge modes have infinite lifetime then within that model, right? But that's sort of simpler cases of topological order where you don't have anything non-abelian, and eventually these are interesting, but not as useful as this non-abelian stuff. Right, yeah. Yeah, you have to. Braiding is a whole difficult story anyway. So if you want to move stuff around, right, then you don't work with a static Hamiltonian, but you change the Hamiltonian, and that might mean that you every now and then you create resonances. It's actually very difficult. So if you move extremely slowly, you will allow resonances to happen, and everything delocalizes. So you have to move more quickly so that this doesn't happen, but you cannot move too quickly, otherwise, you make also transitions that you don't control. So whether there's a sweet spot where you move just at the right speed and nothing happens, that's an open question too, I think.